Hello guys, good day. So today I will be showing you a computational exercise on how to get or determine the value of the equivalent length factor K uh, given a brace frame or a non-sway frame on which the orientation of the strong axis is parallel to the plane of bending as shown in your figure here. So the dimensional and section properties are already given here as far as the moment of inertia on the strong axis is concerned, and the length of the members are also uh, defined as shown in the figure. So the computation for the equivalent length factor K is uh, actually based on the determination of the relative stiffnesses of the column with respect to the beams at a certain joint. So the formula for the stiffness ratio, or the relative stiffness given by uh, the value of psi equivalent to the summation of your uh, stiffness or rigidity all over L of the columns with that of the summation of the stiffness of the beam. Or if the modulus of elasticity for the frame members are the same or constant, then this formula here will simply be reduced to this. Okay, so the simpler formula is summation of I over L of the columns all over summation of I all over L for the beams gives you the relative stiffness at the joint. So for the alignment chart or normal graph, we will be using this AISC uh, graph, no, both for non-sway and sway frame. But for this particular exercise, we're only going to use the non-sway frame graph as stated in the problem. So for the equations, which are referred to the British standard, we have here several equations upon which your K value may be determined, taking into consideration the values of psi mean for the unbraced frame and the values of the individual psi 1 and psi 2 for the brace or the non-sway frame, wherein again the value of psi is simply same as the formula as used as defined in our relative stiffness uh, at every joint, which will be used on the alignment chart. So take note that for a pinned, okay, a pinned joint, a special formula here equivalent to K equals 2 plus 0.30 psi is defined since when taking the average, okay, of the value of psi for the mean uh, for the pin joint, the summation for the stiffnesses on the beams will yield to a zero value. Hence, your psi I will simply be a value that is undefined. So just to take care of such misbehavior, your K for such a condition is given by this formula here. So for the solution of this particular problem. No? So the first step is to compute, no, for the relative stiffnesses given these properties of the moment of inertia and length. So these are the moment of inertia. Okay, and if we compute the relative stiffness at the joints concerned, we all need to look at the figure, since your required columns in particular are only the EF, FG, and KL columns, which are this one. We have actually 3 columns upon which the effective length factor need to be determined. Hence, the joints G, F, and E, including joints KL, are the ones that are needed to take the value for the psi variable or the psi parameter. So we need us to determine psi E, F, G, K, and L on the basis of this formula. So we just plug in, okay? All we need to take note is that for pin connection, your relative stiffness is an undefined stiffness equivalent to infinity, since the summation of EI of the column all over the summation of EI for that pin will be equal to 0. Okay, so at a certain joint wherein this pin end will actually give you no beam resistance. Okay, so there's no beam resistance provided in this particular juncture or joint. Hence, your psi for a pin-ended column will simply be undefined. So for the next column wherein psi f is to be taken, so we just refer to the figure, taking note that at F you have actually 2 columns and 2 beams that are connected. Okay, connected at this particular joint. Hence, we simply sum up the stiffnesses, or the stiffnesses of column EF and FG, and divide it with the sum of the stiffnesses of column BF and FJ, given by this formula. Okay, so this is IEF over LEF plus IFG all over LFG. So these two here are the column members, and these two here are the beam members at the joint. So in order to make some check, okay, it is proper to take note that at the joint F, all of these subscript must contain or all of these parameters must contain the subscript F for us to be sure that the properties taken from the given data are correct and accurate. Okay, so automatically, if I'm going to use MathCAD, I will simply be obtaining the value of psi f to be 0.757. So for joint G, okay, so we also have two columns, which are columns FG and GH, and two beams, which are beam CG and GK. So your joint G becomes your focal joint. Therefore, all the parameters involves the G as your subscript. So this is IFG. Again, these are for the columns, okay? And these are for the beams. And again, automatically using a computational software, you will eventually obtain directly the value of psi g, which is 0.65. So for joints K and joints L, psi K and psi L, notice that the number of beams and columns are not the same with that of joint F and G, because at K, the number of columns are only 2, while the number of beams is 1. Okay, so at joint K, you have 2 columns stiffness to consider, while you have only 1 beam stiffness to consider. And for joint L, you have 1 column stiffness to consider and also 1 beam stiffness to consider. Okay, again, automatically if I plug in the value of these column stiffnesses, relative stiffnesses, and this is the beam stiffness here, I automatically obtain a value of psi k equal to 1.215, and I have only 1 column at joint L, 1 beam at joint L to consider. Automatically I obtain a value of 1.448 for joint L. Okay, so remember that again, the subscript L here must be contained on the parameters involved in the column and beam stiffness. So how to use the nomograph in the determination for your equivalent uh, length factor. Okay, so the procedure is just to plot, okay, the value of your psi at one end. So if this is a column EF, I have a psi E. Okay, I have a psi E here and a psi F there. Okay, so you can actually interchange the position of psi and psi F, it doesn't matter, but all we need to take note are the values of psi E and psi F. Okay, so if I look into my nomograph, your A and B here refers to the joint to consider. Okay, so these are now joint, okay, at the column ends. Okay, so if I take psi A as my psi E and psi B as my psi F, I simply plot infinity, and here it is 0.757 or 0.76. Okay, so I have now a value equivalent to infinity and then 0.757. So if I look into my K line, so my value of K here is approximately in between 0.8 and 0.9, okay, or simply around 0.85. Okay, so my value here for K is 0.85. So if I'm going to use the equation, so the equation for a brace frame, okay, is this one here. So I'm going to consider two equations, and I'm taking the smaller of the two values. Okay, so since psi 1 is my psi e and psi 2 is my psi f, then psi e is infinity, and since this cannot exceed 1.0, then this formula fails in this particular uh, situation. So I have to use the second formula, 0.85, 0.05, as my option. So in this particular equation, so my k is actually a very big number, so I cannot use this value. Hence, the second formula is the one to be considered. If I take the minimum of psi e and psi f, I get the value of a psi f instead, multiply it by 0.05 and add it to 0.85, which is 0.888. And if I compare and take the smaller of the two, of course, this will actually govern, and definitely my final value for k, EF, will simply be equal to 0.888, which is a little bit higher, okay, compared to the k value obtained from the nomograph. So using the same principle for column FG, I simply take psi F and psi G, which is equivalent to 0.757 and 0.65. I use my nomograph and alignment chart. So this is 0.757 and 65. So I just plot 0.757 and here my 0.65. So my k value crossing the k line here becomes more or less 0.725, okay, or 73 as given here in the lecture. Okay, so if we use the equation, so KFG 1 and KFG2, using the two formula, take the sum of psi f and psi g, and then multiply it by 0.75 and add it to 0.7, you get 0.77. And if I get the minimum of the two, which is 0.757, or sorry, 0.65, multiplied by 0.05 plus 0.85, I get a 0.883. So I take the smaller value, this is 0.77, comparing it now with the nomograph value of 0.73. Again, slightly bigger than the first method here. So for column KL, so this is KL. There's a slight error on the lecture, so this is a KL column. Using the nomograph, we have the psi k equivalent to 1.215 and psi l equivalent to 1.448. So your KKL was obtained to have a value of 0.80. If you look into this graph, so this is 1.215 and this is 1. Sorry, they were interchanged, no? So it doesn't really matter if you use the left or the right value, so it will just give you the same answer. So this is the 1.448 This is the 1.215. So your K value here actually intersects the K line at 0.80. So that is your value of KKL. And for your equation, okay, we again compare the two equations here for K1 and K2 and take the smaller value 0.833 will be the value for your KL, KKL using the equation. So it is again slightly higher than 0.80. So to wrap up the uh, the values, we therefore have a pattern, no? In which your nomograph values for K is slightly less than the K values using the equation. Okay, so if this is now a comparison between the effective length, we can say that this, okay, is more what? Which is more conservative. So this is now your less conservative value, and this is the more conservative value. Okay, since your effective length factor K is more conservative if we assume it to be having a value of 1. Okay, so this is now your comparison between the use of the two methodologies. I'll see you in the next video for the other examples uh, concerning beam column problems. Thank you very much and have a nice day.